So, today we will be discussing electromagnetic waves in interfaces and layered structures. We have seen the wave propagation in isotropic medium, anisotropic medium, and also at metallic conducting medium. With that background and knowledge about the propagation characteristics of electromagnetic waves, we will now study the waves at interfaces, their reflection and transmission properties, and we will see that the waves can have two different configurations or an admixture of both the configurations, and we will call them the T and Tm polarization or the S and P polarized wave. Then we will look at the reflection and transmission properties of the P polarized wave in terms of the amplitude reflection, amplitude transmission, and we will try to study this particular P polarized wave in little more details, so that the knowledge can be carried forward to the discussion of S polarized wave and a comparison of both the polarization properties of the electromagnetic waves at the interfaces. So, in order to do that, we will assume the properties of the media who are involved in forming the interfaces. This would be non-absorbing. The individual media will be isotropic and homogeneous. Now, let us consider the plane electromagnetic waves at the interface of two dielectrices, and these two dielectrices are characterized by the properties, the permittivity and the permeability as epsilon 1 and mu 1 for the first medium, that is one of the media, and the respective quantities epsilon 2 and mu 2 for the other media. So, let us first consider oblique incidence at the interface. Look at this figure. You have a wave which is incident at the interface and it gets reflected, part of the wave is transmitted. Let us consider that the magnetic fields are perpendicular to the plane of incidence. By plane of incidence, we mean this plane. So, the magnetic field lines are out of the paper, that is perpendicular to this board, and electric fields are lying in the x z plane. Such a configuration is called a P polarized waves configuration. This is all with respect to the structure, the name P polarized, because each field, that is the magnetic field, is parallel to the interface. This is the interface plane, this vertical plane is the interface plane. Since the magnetic fields are vertical, are parallel to the interface, that is why it is also called TM polarized, that is transverse magnetic field polarized wave. So, with this configuration, we will now study the reflection and transmission properties, but we also have to define the angles of incidence, angle of reflection and angle of transmission, that is refraction, as theta 1, theta 2 and theta 3. K 1, K 2 and K 3, these are the propagation vectors along the incident direction, refracted direction and along the reflected direction. So, with this configuration, the wave that we will discuss is the TM polarized or P polarized wave. There could be another situation, just complementary situation, that now that the electric field is perpendicular to the incidence plane, that is the plane of incidence, that is the vertical plane, that is out of the paper, and magnetic fields are lying in the xz plane. Such a configuration is known as S polarized one. This is also called T polarized transverse electric field polarized wave, because the electric fields are parallel to the interface. So, initially we will look at the properties of the medium in terms of the reflected and transmitted rays. Let us consider the electric fields, plane wave fields associated with the incident wave as u1 e to the power of I omega t e to the power of minus I k 1 r. K 1 is the propagation vector along the direction of incidence. E2, similarly we have an expression, that is e to the power of I omega t e to the power of minus I k 2 dot r, and likewise for the third part, that is the reflected part, we have this expression. So, these are the plane wave expressions for the electric fields in three different places, that is the incident wave, the refracted wave and the reflected wave for the case of TM polarized wave. Now, E fields at oblique incidence, we have these electric fields and each of them and also the magnetic field components will satisfy the wave equation. This we have seen earlier. Now, V square you can replace by n square by c square, where n square is the refractive index of the medium involved. From this we can write down this equation in terms of k square, that is second order derivative of this electric field in the plane wave form will give you minus k square into E, and this del 2 E del t square will give you minus n square omega by c square into omega square. Therefore, you can equate these two, that k square equal to omega square mu epsilon. This means that for k 1 this will be omega square epsilon naught mu 1, omega is the frequency which does not change whether it is reflected, refracted, and k 2 square from here will come out like this, omega square epsilon to mu 2, and for k 3 square we have this expression, but because the medium 1 and 3 in our assumption they are the same medium, that is the first medium, that is why k 3 square is equal to k 1 square, and we will use this property when we will be discussing further. Now, let us consider few example cases. First is in the case of p polarized wave, that is the present configuration that we have undertaken, the boundary conditions are the tangential component of the electric fields must be continuous across the interface. The tangential component, that is this component and this component, the tangential component, tangential with respect to the interface, they must be continuous. So, we resolve this electric field into two parts, that is one is the longitudinal component, the other one is the transverse component. And so, for the incident wave we write E 1 z, which is because this vector is directed in the negative direction of z, this is your z axis, this is your x axis, and perpendicular to this plane is the y axis. Therefore, E 1 z equal to minus E 1 cosine theta, it is very clear. And similarly, for the reflected wave you have minus E 3 cosine theta 3, which is the component, tangential component of the reflected wave electric field, and also for the transmitted wave, the refracted wave, the tangential component will be equal to, all of them are incidentally in the negative direction of z. So, these all tangential components with minus signs will be put together. So, we can write this tangential components continuity condition, that this incident electric field tangential component, reflected electric field tangential component will be equal to the transmitted electric field tangential component, that is E 1 z plus E 3 z equal to E 2 z. So, they must be continuous across the interface, that is at x equal to 0 at this point. Let us see now k dot r in general is equal to k x x, k y y is the plane. So, this, because we are considering the refraction at x equal to 0. So, x equal to 0 gives you k dot r equal to k y y plus k z z. Further, because k y, because if you look at the configuration, there is no y component of the electric field. The magnetic field is purely along the y direction. So, there is no y component of the electric field, that means k y equal to 0. As k is as k is in the x z plane. So, we get this equation, that is we connect all the three components through this equation, that is E 1 cosine theta 1 e to the power of I omega t e to the power of minus I k 1 z z plus similar expression for the reflected wave k 3 z z equal to this, the expression for the transmitted wave e to the power of I k 2 z z. Now, this equation will be valid for all times, and for this validity it is required that e to the power of I k 1 z z, this term must be equal. Therefore, we directly conclude that k 1 z equal to k 2 z equal to k 3 z, but k 1 z is k 1 sin theta 1, k 2 z is equal to k 2 sin theta 2, and k 3 z will be equal to k 3 sin theta 3. Therefore, each of them are equal to the other. So, k 1 and k 2, because they refer to the same medium, we have seen that k 1 equal to k 3. Therefore, and this is equal to omega under root of epsilon 1 mu 1. So, from here we immediately conclude that k 1 sin theta 1 is equal to k 1 sin theta 3. That tells you that sin theta 1 must be equal to sin theta 3. So, that is theta 1 must be equal to theta 3. So, this is nothing but our old law of reflection, that the angle of incidence must be equal to the angle of reflection. And also from the above condition, k 1 sin theta 1 is equal to k 2 sin theta 2. So, when we connect the two media, that is mu 1 epsilon naught and mu 2 epsilon 2, that is k 1 and k 2. So, therefore, from here, because k 1 is k 0 n 1 sin theta 1 and k 2 equal to k 0 n 2. So, n 2 sin theta 2, they must be equal to some constant beta tilde, which is an invariance of the combination of the medium. So, therefore, this shows the Snell's law, which is again our old law, that is the law of reflection and refraction. Okay. Now, so far all that we have discussed is that the continuity of the electric field, the tangential component of the electric field across the interface, which has given us this equation E 1 z plus E 3 z equal to e to z at x equal to 0. If we use this condition that e to the power of I omega t, e to the power of I omega t and e to the power of I omega t here all are same, then we can write down the same old expression which we have seen earlier. In this form, we will remove this e to the power of I omega t. Therefore, and also we will use the relation k 1 z, k 2 z and k 3 z, all of them are equal. They are the z component of the tangential component of the propagation vector. So, k 1 z, k 3 z, k 2 z, all of them are equal. So, you can also eliminate this term e to the power I omega t, e to the power of I omega t, e to the power of minus this term and this term. So, then we end up with a reduced form of this continuity equation, that minus E 1 cosine theta 1, which gives the expression for the electric field for incident wave, reflected wave, which will be equal to the electric field component of the transmitted wave. Now, we will consider the other condition, continuity condition, that is the displacement vector across the interface, the x component of the normal component of the displacement vector will be continuous, that is d 1 x plus d 3 x equal to d 2 x. Now, d 1 x will give you epsilon 1 E 1 sin theta 1, and similarly for d 3 x we get, because epsilon 1 and epsilon 3 they are the same. So, we write epsilon 1 E 3 and sin theta 1. We have seen that theta 1 and theta 3 they are also equal. So, we can write this left hand side in this form, and for the right hand side d 2 x we will write epsilon 2 the permittivity of the second medium, the electric field component and sin theta 2 in terms of that. So, this is the second continuity condition, that is the normal component of the displacement vector will be continuous across the interface. So, we have two continuity conditions, and we will put together these two conditions to see how we can extract some relationship for E 1 and E 3, E 1 and E 2. So, in summary, we have this electric field continuity condition, and for the displacement vector we have this continuity condition. This one has given you this equation, whereas the equation for the continuity of the normal component of displacement has given you this equation. Now, we will do some algebraic manipulation with these two equations, and we will see how the electric field components are connected with the incident field to the refracted field, incident field to the reflected field. Now, I have these two equations. To do this algebra, let us first multiply this first equation with epsilon 2 sin theta 2, and the second equation we multiply with cosine theta 2. As a result, you will see that this first equation will become, this first part will be minus epsilon 2 E 1 sin theta 2 cosine theta 1. Here also you will get epsilon 1 E 2 cosine theta 2 sin theta 1. So, you can add both of them. If you add both of them, then you can see this equation. Just by adding these two, you can see this, because they will cancel. So, from here if we arrange in a way that all the electric field E 1 are on the left hand side and E 3 are on the right hand side, then you can write in this form. So, that we can take E 1 bracketed out from this expression, E 1 we will take out. So, we can write this from this equation, E 3 by E 1 is simply the ratio of the sine and cosine components in this form. Therefore, E 3 by E 1 we can readily write down in this form, but what is E 3 by E 1? E 1 is the incident amplitude of the electric field, whereas E3 is the reflected amplitude of the electric field. Therefore, the amplitude reflection coefficient which is given by E3 by U1, we will call this RP, because we are working with the p polarized light, that is the TM polarization. Therefore, RP is equal to E3 by U1. This we can write directly in this form in terms of the permittivity constants of the permittivity values of the two media involved, like sin theta 1 cosine theta 2, sin theta 2 cosine theta 1, and the same expression at the bottom, but with a in the denominator, but with a plus sign between them. And because E1, the permittivity for this dielectric is nothing but the square of the refractive indices. So, we can write E1 equal to N1 square and epsilon 2 is equal to N2 square. So, this is the other form of this equation for the amplitude reflection coefficient for the p polarized light RP. Okay. So, this amplitude reflection coefficient, now we have seen that this equation, and we have also seen that we have used this epsilon 1 equal to N1 square, epsilon 2 equal to N T square, and we have got this form, which is now the amplitude reflection coefficient is in terms of the concerned refractive indices and the angles of incidence and angles of refraction. So, these are the things which are going to decide the amplitude reflection coefficient. So, it primarily depends on the refractive indices and also the angle of incidence, which generates which yields the angle of refraction also, because they are connected by the refractive indices properties. So, amplitude reflection coefficient we can even write in some modified form or reduced form, rather we can say that RP is equal to this in terms of the refractive indices, but now N1 sin theta 1 is by the Snell's law. We have just now seen that N1 sin theta 1 for the first medium, this the angle sine of the angle with the refractive index is equal to N2 sin theta 2 for the second medium. Therefore, using this connection we can again rewrite this equation, that N1 sin theta 1, if we remove 1, that will give me N2 sin theta 2, which will also appear here N2 sin theta 2. So, we can take outside from this numerator one N1 sin theta 1 or N2 sin theta 2, and likewise from the denominator we can also take out one N1 sin theta 1 or N2 sin theta 2, and they will cancel outside. As a result, you can write down this equation in this compact and very small reduced form, that the amplitude reflection coefficient for the p polarized light can be written as N1 cosine theta 2 minus N2 cosine theta 1 divided by sum of these two factors, N1 cosine theta 2 plus N2 cosine theta 1. And this equation is very often used for calculating the Fresnel reflection coefficient, energy reflection coefficient, etc. Okay. Now, for calculation of the energy transmission amplitude transmission coefficient, we again work with those two equations, that is this continuity condition for the electric field and for the normal component of the displacement vector, and this time we multiply the first equation with E1 sin theta 1 and the second equation with cosine theta 1. Then if we add, you can see from here, you can rewrite this equation as this twice E1 epsilon 1 sin theta 1 cosine theta 1 and so on, which is equal to 0, because here we try to eliminate E2 from both the equations, and then if you bring all the u1 to left hand side and e3s to the right hand side, then again you can write in this form. The equation can be written in this form. Then proceeding in a similar way, by multiplying this, we add and rearrange, we can write down this equation. This step we have shown earlier. So, E2 epsilon to E2 cosine theta 1 and E2 U1 cosine theta 2. Then we will get the amplitude transmission coefficient, that is E2 epsilon 3 E2 cosine theta 1 sin theta 2 this. So, that means this time E2 and E1 they are now connected. E2 and E1 they are now connected by this equation. Thus, the amplitude transmission coefficient, which we will write Tp for this p polarized light, and we can write E2 by U1 because it is the ratio of the incident electric field amplitude to the transmitted electric field amplitude. So, we end up with this equation, which is this expression, which is in terms of the permittivity constants, and this Tp in terms of permittivity constant, this expression can be written in terms of the refractive indices in the same way as we have done in the case of reflection amplitude coefficient. So, twice n 1 square sin theta 1 sin cosine theta 1 divided by this denominator, and we will again use Snell's law to this expression to have a reduced form of this equation. So, if I use Snell's law for this equation, you can see that n 1 sin theta 1 will be equal to n 2 sin theta 2. So, from both the places we can take out n 1 sin theta 1, n 1 sin theta 1, here n 2 sin theta 2 they are appearing. So, you can take out, and n 1 sin theta 1 from the numerator you can take out. As a result, you will get T p, this amplitude transmission coefficient in this reduced form, that is twice n 1 cosine theta 1. This expression is also very often used in Fresnel reflection transmission amplitude coefficient calculation. Therefore, to summarize that, we have amplitude reflection coefficient in the form of this, or in terms of only the refractive indices and the angles of incidence and angles of refraction. We can write this equation, and for this we can write the transmission amplitude in terms of this equation. So, till now we have been able to see how this electric field amplitudes are related to the from the incident wave to the reflected wave and to the transmitted wave in terms of the amplitude reflection coefficient and amplitude transmission coefficients. And then we will discuss more about the details about the energy transmission, Poynting vector and other things in this discussion in the next section. So, to summarize the discussion, we have seen the waves at interfaces, particularly the reflection and refraction. We have also seen the both the configurations, that is TM and TE polarizations, how the electric field magnetic fields will be oriented with respect to the structural geometry, that is the interface plane, the incidence plane, and we called this TM wave, TM polarized wave as P polarized wave, and this T polarized wave as S polarized wave, and we were discussing the Fresnel reflection coefficients, amplitude reflection coefficients for P polarized wave, and we will continue this discussion in the next section. Thank you.